is on. So next speaker is Marris, working with Luca, I suppose, and yeah, titles on display.
Okay, yeah, hi everyone. So yeah, I'd like to start by thanking the organisers for putting on a nice conference. It's been really interesting. So I'm going to be talking about first passage problems on correlated random walks, and specifically some work that I developed during my PhD with Luca Giugioli to extract these first passage distributions on different lattices, specifically with boundary conditions. Okay, so these are the lattices that I want to think about. I think the hypercubic lattice is very well known. So that Z here is the coordination number, or the number of sites that the walker is able to jump to. So in the square, it's 4. The hexagonal lattice, you can think about it as moving from centre to centre of the hexagons. So you've got a coordination number of 6. And the honeycomb lattice is perhaps the most complicated. It's got a coordination number of 3. And the reason I say it's the most complicated is just because you've got these two different site types. You've got the negative site and the positive site. And you can just see there's just slightly different movement statistics on those sites. So yeah, it adds another little layer of complexity there. So what do I mean by the persistent random walk, or the correlated random walk? Well, it's a one-step memory dependence. So basically the idea is that we have a probability that the walk continues in the direction that it last travelled. So if you look at this schematic here, if you look at the top line, if it follows that red arrow in, then to take another right step is going to persist forward with some probability f for forwards. But on the bottom line, if it follows that red arrow in and then it takes a right step, well, that's a backtrack. So even though it's the same, sort of jumping from the same site, it's with a different probability. So basically, the outgoing probability of the site depends on the direction that the walker enters the site from. The way we keep track of the direction that the walker enters the site from is we use random walks with internal states, sometimes called internal variables, I think. And in my schematic here in 1D, I've decomposed that system into sort of 2 internal states. So basically, you need the number of internal states for the coordination number of the lattice. So I've got my state 1, which is the green one, which is sort of keeps track of coming in from the left or moving right, and my blue state 2, is coming in from the right or moving left. And I've got my 3 probabilities, F, B, and C. And the reason I just say it's the probability of moving in the same direction as the last movement and not the last time step is just because we allow this probability of waiting in the site, C, and that doesn't change the direction you move because you just don't go anywhere. So in general, what we're going to be solving for, at least in the occupation probability, is these column vectors of occupation probabilities. So that's the occupation probability being in state 1, and then the occupation probability being in state 2. And if you want the occupation probability of the whole site, you simply have to sum them up, or you can extract them individually from the column vector if you would like. And once we've written it in this way with internal states, it's fairly straightforward to write it as a master equation, which is on the board there. And in general, when you're solving it, it's easier to write this in matrix form. Okay, so what do these solutions look like? Well, in the unbounded case, it's here. So you can write it in its inverse Fourier transform form, or lattice Green's function form at the top there. And then with a little bit of effort, you can actually solve that integral, and you get that solution in the middle. And there's a couple of things I want to point out. That if f is greater than b, the probability of persisting forward is likely, so you're going to more likely to go in the direction that you were previously going. If f is less than b, we're in the anti-persistent regime, you're more likely to turn back. And if f equals b, we're in the diffusive limit. So you can see actually quite a lot of things cancel in that equation in the diffusive limit. And it's a fairly straightforward exercise to show that this reduces down to the known generating function for the diffusive lattice random walk in that case. Just the other thing to note is this alpha 1 and alpha 2. You have to make some choice about the direction that the water entered the initial site before time started. So we just assume some probability that it came in from the left with alpha 1, some probability it came in from the right with alpha 2. Okay, so what are the boundary conditions that I'm going to consider? Well, in this talk, I'm going to think about the periodic boundary condition, which I'm sure everyone's knows, it just wraps around to the other side if you go off the domain, and the reflecting boundary condition, and specifically what I call the bouncing reflective boundary condition. And what I mean by that is if you get to the edge of the domain, you can think about a barrier between maybe n and n plus 1, where n's the size of the domain. So you the way I think about it is you come out of n, you hit the barrier, it invokes a change of direction, and then it allows you to basically bounce back from the state below. So you get to the wall, you hit it, and then you sort of enter the other state, and it allows you to continue your persistent trajectory back into the domain. So the way we can go about putting these boundary conditions on, there's 2 ways. We can use the method of images, and I've just shown here the periodic case, and Barry Hughes' excellent book sort of teaches us how to deal with equations like that. And then there's another method that we call the squeezing method, which was developed by Zia Kalai in this J4Z paper in 2012. And again, I won't go over the details, but I'm happy to talk about it afterwards. But basically the idea is if you find your periodic propagator and you stick it into this formula on the screen, then you're able to sort of get out a reflective boundary condition, which is the one that Chandrasekhar first thought about back in 1943. So what do these solutions look like? Well, mathematically, on the bottom here, I guess the thing to point out is that this lambda matrix pertains across both solutions. It's just the functions inside that matrix are evaluated with a slightly different argument depending on the boundary condition. And I'll talk a bit about this lambda matrix in a couple of slides because it's actually very general, its form across all dimensions. And then pictorially, you can see in figure A here, we've got these two pulses of probability at short times that are sort of persistently going away from the initial condition. And then as diffusion begins to take over, those peaks sort of flatten, the distribution broadens. And as we might expect from finite space, we end up with this steady state distribution. I guess another thing to note is that we've got this slight bench-like structure with a dip at 1 and 51, which is the size of my domain here. And that's just because this Chandrasekhar boundary condition pushes you back. So if you leave from a boundary between 1 and 0, it pushes you back to 2 instead of 1. So that's why we've got this slight dip at 1 and 51. And just to note that if we don't have a uniform distribution over the way that we can get into the site initially, so if alpha 1 is bigger than a half, that basically says that we were more likely to have started our movement going in one way. So if we're in the persistent regime, we're more likely to carry on that way, and then we can get out some asymmetric occupation probabilities. Okay, so we can play the same game in higher dimensions. We can write a general matter equation, and those 3 arrows are skipping out quite a lot of derivation, but that's the answer anyway. And this is the occupation probability, and it's valid in arbitrary dimensions in both periodic and reflective boundary conditions. And again, you can see I've got this lambda matrix. It's bigger now, and the arguments still depend on which boundary condition we're interested in. And you can see we've got these product of G functions in the middle. And basically, the reason that we can get this out is that we can write the boundary condition for each internal state. And then when we sum them up, the boundary condition over the whole site, we can see that actually the boundary condition acts, it's exactly the same as the diffusive boundary condition. So the method of images, the image set that you need to implement these boundary conditions was derived in Luca's PRX paper here. So we can follow through the algebra and get them out. And we just have a product because you can't really interact, well, you can't interact with two boundaries at the same time. So if I'm moving north, south, and east and west, I'm interacting with the east-west boundary, I can't be interacting with the north-south boundary. So these image sets are independent of each other. Okay, so I said this lambda matrix is quite important. So what does it look like? Well, this is the 2D square case. But in general, it has these properties. So for Bravais lattices, so for the hexagonal and the hypercubic, it's always of size z by z, where z is the coordination number. The diagonal elements represent remaining in the previous state, and I can do that by persisting forward. So that's why we get these f's, and I can also do that just by not going anywhere. So that's why we have these plus c's. We've got alternating off diagonals, which represent backtracking movement. And all the other elements in the row represent sideways movement, which I've just used L for lateral movement here. And in fact, we don't actually have to have these L's as uniforms. We don't have to have the probability of turning left to be equivalent to the probability of turning right. And it's something that we've relaxed as an example in the hexagonal lattice. Again, I'll skip over quite a lot of the details, but we've implemented a periodic boundary condition that we derived in this PRE paper. And again, we have our lambda matrices, which are now 6 by 6. And when we relax this probability of turning left to be turning right to be equal, and what I've actually done here is I've said, well, the probability of persisting forward or making a left turn is much higher than all the other movement options. Then we can get out of this sort of chiral motion where we sort of pick a general persistent direction to go in, but we get loopings. So this is a simulated trajectory of the behavior that this equation can govern. Okay, so how do we use this to extract the first passage probability? Well, we use a defect technique, and basically the crux of the method is that we want to put traps on internal states and not over the whole site itself. And the reason for that is if we look at the schematic on the bottom left there of the screen, we only need to put one trap in the system because we physically cannot get into that site from the right. If we can't go past it and make a turn and come back in because we can't go past it because we get absorbed out of the system once we reach that point. However, if we're in a periodic boundary or in general in higher dimensions where we can get into the site from all directions, then we put a state in all of the state. We put a target in all the states of the target site. So the general idea is that we solve the target first passage problem from a localized initial condition in state 1 in that green state. And the first passage problem, again, equivalently from state 2. We know that they're independent of each other. You can't start in 2 locations. You have to start in one or the other. And then we can sum them up, and we have a weighting constant alpha 1 and alpha 2, which just says how many started in the top one and how many started in the bottom one. So again, that's the master equation that governs the process. We have an initial condition that just says, did I start in a trap state or not? And again, you follow through the algebra, and this is the solution that we get. So mathematically, it sort of says what I described. So that's internal sum is the first passage problem to multiple targets. The external sum is keeping track of all the initial states that we could start in. Then we have our alpha weighting, which keeps everything normalized. So what does this look like? Well, here's some plots. So dots are representing stochastic simulations. The lines are my analytics. So you can see there's very good agreement in all cases. And I guess the thing to note is that these distributions can be bimodal. And in fact, we can actually identify 2 different sort of sets of trajectories that cause these 2 peaks. So we've got those that go straight towards the target. We've got those that go away from the target, interact with some boundary, either taking a periodic loop and back in, or bouncing off the reflecting wall and back past the initial condition to the target. And you can see this most clearly in the 1D both case. So we've sort of biased the trajectories to start going away from the target. So we get this very high peak at short times in the periodic case, where it's able to utilize that periodic boundary to find the target very quickly. And in fact, the second peak in the periodic case here corresponds to the exact same timescale as the first peak in the reflective one, those that have gone straight towards the target. And the second peak just poking out at later times for the reflective ones, those that have gone away, hit the wall, gone past the initial condition, and come back. So we can play the same game in higher dimensions. This is the hexagonal case. I won't go into too much detail about it, but you can see that we get these nice multimodal distributions. The thing I want to focus on a bit more is the directional first passage. And what I mean by that is it's the first passage probability I enter a site and I'm traveling in a specific direction. And the way that we can do this, as I said, the internal states keep track of the direction you traveled. So if I just put an internal state, a target in one of the internal states, then I can ask this question. And you can see that at short times when it's the direct trajectories that are dominating the distribution, this direction matters. And that makes sense, especially in the persistent limit. If you think about going straight towards the target, you're much more likely to hit it in your persistent direction than you are to go just past it and make a backtrack just at the right time to come into the target. But at long times, when the sort of diffusive trajectories are taking over and they're much more indirect, it becomes equiprobable to enter the site from any direction. Okay, so in the last sort of 3 minutes, I guess, I want to explain how we've used this to as a model for foraging behavior in this species of ants. I think it's pronounced Aphinogaster senilis. And essentially, we did some work with our experimental collaborators, Paul Fernandez-Lopez and Frederick Bartemus. I don't know if you can see, but in the middle of this picture, there's an ant, and it's moving around on this honeycomb lattice. And we basically said to them, okay, well, can you work out the probability that if I turn left in the previous time step, do I turn left again in the next time step? So now my persistence is more in like the way I'm turning, as opposed to the direction that I'm going. And they said yes. And they actually were able to identify 2 different types of ants that had 2 different movement statistics. They had the scouts and the recruits. I believe the scouts go out and search a lot further away, and the recruits stay closer to the nest. Anyway, so we took the Montreux embedding of the honeycomb lattice in that figure I there. We decomposed it a bit further, and we put our internal states to represent the direction that we entered the site from. And again, we can solve for lots of stuff. And just the thing I want to point out is the spreading mechanism. So we've got the mean squared displacement and the mean number of sites visited. And you can see in both cases that the scouts, those ones that go further away from the nest and they're looking for food sort of further away from home, they explore the space a lot more efficiently than the recruits do. However, both cases are more efficient than just a standard Brownian walker over this trajectory. And in the inset here on B, you can just sort of see the range of movements that this model can get out. So in the green line with the black dots, that's just the diffusive limit. So the probability of making all the turnings is completely uncorrelated to your previous movement. And then we have this circular one, and that's sort of maybe what you can think about as like a ballistic limit in this honeycomb setting. So that's if I turned right, I have probability 1 of turning right again. So in that case, you're just going to chirally go around 1 hexagon for all time. So that's why this mean number of sites visited very quickly plateaus at 6, because it visits all 6 in the site, and then it just keeps exploring the same space forever and ever. Okay, so with that, I'll end. And if you're interested in anything I've said, these are the references. Most of the stuff is in that third one in the New Journal of Physics paper. So yeah, thanks for listening.
Okay. Yes, Sergey?
At the very beginning, you introduced 2 master equations, discrete force in time and space.
Yes.
Have you looked at a long time large scale limit of this? Like diffusion approximation.
Yeah, I mean, I guess so. I guess I haven't done it, but I'm sure, I mean, you can get out the occupation probability solution, so I guess you can always take the T infinite limit there, and I guess you get what we would expect, so this uniform steady state at long times, so it's going to always go to that in this finite space. Is that sort of your question?
No, it would be interesting to see those equations in time and space.
Okay, yeah.
Okay, no further urgent questions, then I suppose lunch is waiting, so let's thank the speaker again and all speakers.